Hello everyone. So my name is Yvan, and today I will speak about basically how experiences in fuzzing area and especially against network services with custom protocol. And for this we use SAP. Just one slide about me. Like I said, my name is Yvan. I work for Onapsys. This is a security a company dedicated in ERP security and of course of SAP. And my daily work is to find vulnerability in SAP system. So I'm already involved in few vulnerability, and all these vulnerability come from SAP components, and so that's enough for me. Yes. Yeah, an issue with you can hear me? It's fixed? It's better? Okay. Do you want to? Okay. So, this is the agenda for today. So very quick introduction, and after that I will just try to explain step by step how journey in this fuzzing area. As an introduction, the true story was in my last conferences 2 years ago. I was on a diner and a diner speaker, and I discussed with someone, and the guy was very, very poor, very skilled in fuzzing stuff. And he told me something like, hey, when you match your SAP knowledge with fuzzing, I'm pretty sure you will find something. So this is something I put in my mind, and a few months after I was the occasion to work on this subject. So I was curious, of course, and also when I start to try to find out if there are already some research about fuzzing SAP, I didn't find anything. And we think that SAP here, it's a very, very good example, because when you scan for the first time an SAP system, you got something like that. This is for one system. All this port by default is open. Of course, there are some very well-known kind of services, HTTP server, but there are also some few other services who handle some custom protocol that we can call it a black box protocol. And here we will speak about NQ services, IGS, etc., etc. So when we start to try to study, okay, what is the fuzzing, what we need to do, what we need to have, etc. The first thing we understand is we need to have a test case. What we call a test case in this case, it's a network packet we would like to send to the services, and we would like to fuzz this network packet. We would like to mutate this network packet, and that's it. So the first step we understand is to try to grab this packet. So I just have one slide by custom services handled by SAP, and just to explain how we achieve to grab network packet. So the first one is called ICM. This stands for Internet Communication Manager. This is no more than the web server hosted by the SAP system. So just sniff the port, connect with a browser, and you get a lot of packets like that. This is not very complicated. The second one is the NQ. The NQ server manage the log system for an SAP for the SAP instances. So how we perform to have some test case? It just sniff the port 3201 and restart the system. Also restart some instances, and also try to update a table. Like that, we got several packets, and all it's the NQ protocol. So this is a proprietary protocol without a lot of documentation. And one word about the IGS. So the IGS is the Internet Graphical Services. It can do a lot of things. I already worked a few years ago on the IGS services, and it can convert image, generate chart, and etc. So listen on this port, and you get nothing. But if you listen on the local socket in /tmp.substream, followed by the port number, you can grab and sniff a lot of packets. So how to generate packet? Just log in into the system, use the IGS administration dashboard, and then you can perform some activity, generate shard, etc., and you get a lot of packet also like that. The next one is the SAP Gateway. This is a well-known services now. To sum up the gateway, it's the services who can able the SAP to communicate with outside. It could be different kind of target, could be another SAP system. So to have some packet, this is no more than we log in into the system, we launch again the admin transaction for the SAP Gateway administration, and you perform some health check. You perform also some kind of ping between several systems, etc., etc. So like that, we got a few packets about the SAP Gateway. The next one is the dispatcher. The dispatcher, without too many complicated things, the dispatcher handles the user request. So when the user uses the SAP client, named the SAP GUI, it communicates with the dispatcher, and the dispatcher dispatch the request to several work process. So for this one, this is very easy. Sniff the port and log in to the SAP system. You can perform successful login, one login, something like that, and you get a lot of packet to the dispatcher. The next one is the message server. So to simplify, in a SAP system, you can have several instances, and the message server manages the communication between all instances. So you can again sniff the port, and you can log in to the system, because when you log in, the dispatcher communicate with the message server to say, okay, go here or go here, and also you can start and stop one instances in the whole system. So again, like that, we got a lot of a packet from the message server services. Okay, it was the very easy part for us, because we work for SAP for many long times, so we know exactly how to do it. Now we try to jump in. For us, it was a new area. It was the fuzzing area. When we start by fuzzing the packet we just grabbed during the sniffing part, we very quickly we got one big problem. To explain this problem, it's something like that. To sum up the packet, all the protocol managed by SAP services use this kind of feature. So the first 4 bytes of whole packet, it's the size of the content. All right, and this is the same for the dispatcher, end user, etc. So why it could be a problem when we try to fuzz the packet itself? Let me show you with this example. This is a very simple packet from the NQ services. This is kind of end check packet, so very tiny. So on the top left, the first 4 bytes in red, it's the size of the rest of the packet. Okay, so in this case, this is 5D, right? Now imagine a fuzzer or tools or something try to modify the content by adding 1, 2, 3, 4, 5, 6 somewhere. So the size of the content change, but the fuzzer didn't know about what is the first 4 bytes. So it untouched it. And when you send this kind of packet to the services, the very first check done by the services is to grab these first 4 bytes and to compare with the size of the packet you send. And if it's not matched, you get drop, and you never go deeper in the binary. So during our first test, we sent like 10 million tests, and nothing crashed, 0 crashes. It was not the very easiest part. So what we would like, it's something like that. If the fuzzer modifies the content by adding something, also we would like the fuzzer be able to modify any size to match it. So when the service receives the packet, it checks, and okay, the first check is pass, and you can go deeper in the services. It's very important because this problem also guides us to select the fuzzer. Because if we do not achieve to solve this problem, very probably we do not achieve to do nothing. So let's jump to the fuzzer selection. Just imagine it where we are completely new in this subject, and we try to understand, okay, what kind of fuzzer exists, and etc. You get a lot of content, a lot of tools, a lot of articles, a lot of things. And for me, this was completely too much. I don't know where to start. I haven't the time to test everything. I haven't the time to do deep research on it. So what we decided, okay, let's do it step by step. First of all, what is our target? In this subject, our target is an SAP system. And behind the SAP system, behind all services, we speak about the SAP kernel. The SAP kernel is no more like a directory with more than 700 binary. And the size of this kernel is like 800 megabytes. So this is our target. So when you read some article like, just modify this library or this thing, it very probably didn't work on SAP target. So just imagine that this is a very complicated environment, and if you modify one thing, you can break everything without the intention to do it. So the very classical IFL fuzz binary followed by argument 1, 2, this is not an option in our case. All right, now this is our target. Also, we have the any size problem you want to solve. So what we need exactly? First of all, thank you, Captain Obvious. We would like the fuzzer with the capability to work over the network. It could be remotely, it could be locally, but we would like to search for something to it. Secondly, we would like to avoid modify the target. We would like to avoid modify the SAP kernel itself because, again, it could be very complicated. And also, if you modify the kernel and you find a crash, you need to reproduce the crash again, an unmodified kernel, and it could be complicated again. And basically, we don't like complexity. And also, we would like a fuzzer when we can solve the any size issue. So a fuzzer, maybe you can modify, maybe you can add some module to explain that, hey, if you modify something, I want you to modify also the size, the any size. And we look for close to up-to-date tools because we would like, again, to avoid install legacy library or something like that, and we will look for something new. Of course, we think about, let's create our own fuzzer. But remember, this is, when you look on the fuzzing area, what kind of fuzzer already exists, there are a lot of tools, and we would like to avoid, again, to add a tools plus. Because for my point of view, there are too many fuzzer, too many tools, too many things, and first of all, we would like to find, maybe there are already a project who can match our needs. Maybe we need to modify it or something, but that's it. So, of course, we test IFL Fuzz. IFL Fuzz is a very well-known fuzzer. We test it a lot. We try it with the QEMU mode. You try it with a DSOX. We try it a lot, and we never achieve to have very good result with IFL Fuzz. Next, we test IFL Net. This is a fork of IFL, but for network. And again, we never achieve to have results. And just the time million test we send in the first part of the slide, again, the NQ, was done with IFL Net, and IFL Net find nothing. After that, we test the FFW. It looks promising, but again, we do not find an easy way to solve the any size problem again. So the dumb fuzzer just fuzz, and nothing happened. And After that, we test Fuzzotron, and Fuzzotron match, more or less. Fuzzotron was maintained by Dewey, and Fuzzotron was very simple. It's only the source code is like 10 files. It's very simple. It's written in C, and I know a little bit about C. And you do not need to modify the target, etc. This is very, very simple fuzzer. Like you provide the test case, you mutate the test case, you send it to the service, you monitor the service, and that's all. So there are no post exploitation of post analysis, but for us it match. And it match because very quickly we find crashes using this fuzzer. So let's start to use Fuzzotron in the future. So how we solve the any size problem? So remember, the any size is the first 4 bytes of each packet, and what we would like is to be able to modify this size to match the real size of the content. So instead of, as a test case, instead of provide the whole packet, you provide the whole packet minus these first 4 bytes. So the fuzzer mutates the content. Then we hard code in the source code, like, hey, I want to calculate the size and to put the any size at the beginning. So during the research, I did it with a very, very ugly style. So I just modified the source code directly. And in March, Dewey had this feature by default now in Fuzzotron. Basically, you need to update the function. The function is called callback presend in callback.c. By default, this function is empty, and you can put what do you want in this function. And the very interesting thing is this function is called after the socket is open, after the mutation is done, but before the test case is sent. So you can modify and do what do you want in the test case just before send it. So this is an example of the code to solve the any size issue. So the function just takes the socket and the test case, a pointer to the test case, so you have the length of the test case, etc. I just calculate the any size, so the size of the test case, and I put the any size at the beginning, and I merge everything, override the test case, and the packet is sent like that. And we find 3 crashes very, very quickly just by using this kind of code. So this is why we decide to go with Fuzzotron, because it looks like simple, it looks like very flexible, and this is what we're looking for. So of course everything is patched in this patch for this one. Now the next step was something like, okay, now I would like to fuzz not the whole packet, because sometimes the packet is huge. I would like to specify a part of the packet I want to fuzz. So for this part, I will take an example with the RGS. So this is just an example. Of course, we did it for whole other services, SAP Gateway, message server, etc. So this is a RGS packet. It looks complicated, but don't worry, it's not. Because there are some parts you can guess very easy. So you recognize in black on the top left, this is the any size, the famous any size. Then I try to colorize a little all the parts. So there are some headers, there are some table. On the top right in green, it looks like XML, and in pink, sorry, this is an image. This is a BSP in this case. So this packet, if you send this packet to the IGS try to convert the image you provide to a GIF. Okay. But in our case, for example, what we would like is, okay, we would like to only fuzz this part, not the whole packet. We would like to fuzz the XML parts. So it's possible because, again, you can use the XML part as a test case. This is what you provide to the fuzzer. And you can calculate and hardcode the rest of the packets directly in the source code of the Fuzzing. And it's not very complicated to do. And also, as you can see, in the XML part, there are the size at the beginning. And if you want to fuzz only the XML size, the XML parts, you also would like to modify this size to match the mutated size of the XML. And trust me, the mutation sometimes it's it's very, very, very big or very ugly. So to sum up, now we hardcode the beginning of the packet, the end of the packet. We ask to fuzz the XML parts. We calculate the size of the XML part. We calculate the any size of the whole packet. We concatenate everything. We send it to the service and just press the sun, and we will see. So this is an example of the callback.c. As you can see on the left, so this is only the hard-coded part. So this is the beginning of the packet and the end of the packet. Then you can calculate everything, and you calculate the size of the XML, the mutated XML you provide as test case. Concatenate everything, put in as a new test case, and the further send this correct packet to the services. And of course, you can do it for different parts in the packet. For example, you can fuzz only the image, only the header, etc. And also, we did it for all other services. And this time we find 11 more crashes using only this technique to, okay, I want to fuzz this part or this part. So now the number of crashes is 14. It's beginning to be interesting because 14 vulnerability in SAP is not so usual. But let's continue. Of course, everything needs patches in this patch bundle. The next step now, it's pretty obvious, but we would like to explain it. In the protocol of the services, sometimes you want to fuzz not the first packet you send, but the second one or the other one. Just to explain this part, I will use the SAP gateway. So the SAP gateway, very, very simple, something like that. You send the first packet like an check. Hey, hi, hello. The SAP gateway always answers something like an end check back. Then you provide a second packet like, what do you really want to do? Okay? So the hello packet, it looks like that. So it's a tiny packet, not very complicated, and we find nothing on it. Of course, we try to fuzz it, and we find nothing. But the do something packet, the next packet, it's quite more interesting because it's a use packet, complicated, and it looks like, okay, I can fuzz this part, maybe this part, and etc. So what is possible to do again? Because the function callback.c, in callback.c, the function callback presend is, it's called after the socket is open. So you have the socket, you have basically the socket open, and you can communicate with the services. So this is what I do in the first part. I just send the end check. This is hard-coded end check, always the same. I write it in the socket, so I send it, and I read the packet sent by the services. I don't care about it. You can work with it, but in this case, I don't care. And after that, I send the second packet, and the second packet is what I want to fuzz. So like that, it's what we call a setup conversation. Like, okay, I can set up my conversation with the services to reach a dedicated packet I want to fuzz. So we find two new crashes like that, and one in the SAP gateway. So this is the SAP gateway. It's a very, very robust services on SAP, trust me, and one on the dispatcher. And this is the patches. The next one, it's we encounter a big problem. It was what we call a collateral crashes. Let me show you. This is the process list of whole, not whole, but a part of the SAP process. So if you go to the SAP system, you list the process, and this is a tree you can have. This is not very complicated. For example, in green, this is NQ services. So you recognize en.sap blah blah. This is the NQ process who handles the NQ services. And there are several processes like that: the message server, also the SAP gateway in pink, etc., etc. So the ICM in blue and the IGS in orange. So, all right. Another one interesting is the dispatcher. So, in red, the process Bob00DP, like dispatcher, is the process who handle the dispatcher services. And as you can see, the dispatcher is no more like he receives the user request, and the dispatcher dispatch the request to the work process. So the work process is no more than a child process of the dispatcher. All right. Something very very common in big system like SAP. So what's happened? One time we decide to fuzz the dispatcher. So we monitor the PID of the dispatcher, and we configure the fuzzer to send everything to the dispatcher services. And what we got is sometimes one work process restart. When you fuzz something, it's something crash or something restart, very, very probably it's because of us. But you can imagine, okay, the work process restarts. So we look in the log file. So each work process has its own log file. And when we look on the log file, we can see a crash. So yes, the work process crash, and very probably it's because of us. But because the dispatcher, the main process, is still up, the fuzzer never stops. And if the fuzzer never stops, the fuzzer never back up the last packet it sent. So what we call the guilty packet is a malicious packet you really send to crash. It's lost. The packet you would like to extract is completely lost. And of course, the work process crash randomly. Sometimes it's a 0, sometimes it's a 6, etc. And whole work process has this own log file. So we need to figure out how it's possible to work with this log file and not to work with the PID of the dispatcher. So what we did, it's okay, let's craft a script to concatenate all the trace file. Then instead of looking for the PID of the dispatcher, we're looking for the pattern cstack. This is a pattern we look for in the trace file. And we launched everything again, and we completely failed. Why we failed? It's because the fuzzer stopped. Good. Something crashes, but we never able to reproduce the crash with what what the fuzzer backup. Let me explain you. So this is a part of the Fuzzertron source. To be very simple, the Fuzzertron generates 100 test cases, send this 100 test cases, check if the pattern is in the log file. If the pattern is not present in the log file, it just removes this test case and generates a new 100 test case, like that. And what we understand is how crash chain. It's something like the fuzzer sends the packet, the dispatcher handles the packet, forwards the packet to the one work process. The work process handles the request, crash, write this crash information in the log file, restarts, then the log file is concatenated in one big log file, and then the fuzzer finds the pattern. And during this time, more than 1,000 packets was sent. It means the fuzzer gets the crashes information too late. So very clever and smart move. We just change the number of packets generated. And instead of 100, we put like 5,000, 10,000. If you do that, you will lose a lot of performances. But we did it because we observed that the first crash appeared like less than 5 minutes after running the fuzzer. So even if you lost like instead of 5 minutes, you lost time like 20 minutes or 30 minutes, it's not a very big issue. So we find 3 new crashes using this technique. And the last one I would like to share, it's the last one we find. It was in the ICM. So the ICM, it's a web server hosted by SAP. And what we understand is sometimes the ICM use this own child process, and also sometimes this child process can communicate to a work process again. So now we understand that, okay, if we fuzz the ICM services, we also must monitor the trace file of the work process. So this is an example of the very classical HTTP request you can send to SAP. And we made different testing, and eventually we test the cookie. So this is a cookie session. The name is my SAP SSO2. So this is a cookie session, and this is the content, an example of the content of the cookie session. So this cookie session, it's encoded in base 64, then it's URL escaped, then it's put in the cookie header, of course. So to sum up how it's possible to fuzz this part and to get the correct monitor and to retrieve the guilty packet. So what we need to do is to check the collateral crash. So to check, hold the file, and to escape the test case we provide, because basically we provide, as a test case, we provide the binary content of the cookie, not the base64. So we need to craft everything in the callback.c. So it's look like that. So the first part is just to encode in base64. The second part to URL encode. And the last part is to craft the HTTP packet. So hard-coded the post request, hold the header, and put our test case as the content of the cookie, and send the request like that. And we found a last crash. And the interesting part is we found the crash in the SAP common cryptolib. So this library, it's the SAP security crypto and everything. So it was interesting. All right. I have a couple of demo. I'll try. So as I say, everything is not automatized. With Fuzzotron, you need to script something. So this is very, very simple. What kind of script we did? It just like start the fuzzer when it crash, start again, but with the last packet generated. When it crash again, start again, but this time attach the GDB to the services to try to find out the crash detail. So this is no more complicated like that, and that's it. So yeah, it's not perfect, but sorry. So on the top left, on the bottom left, this is the fuzzer running in the loop. On the right, this is no more than a process list grabbed by GDB, because I have some issue to GDB sometimes not stop and something like that. And on the top, this is a list of crashes, the history of crashes I get. So basically, I send this script, at night, and when I go back on the morning, I just take a look on all history I get. So as you can see, it's running on the bottom, and very quickly after a few seconds, a crash appears. So we restart the services. This time we try to replay the last packet, but with some delay to be sure to have the good packet. It's crashed again. So now we take the last packet and we restart the services with GDB, and again send the fuzzer, but we not send the fuzzer, but we just only send this packet. The crash appear, and we get every information and a new line, a new crash history appears. So like that, you have all the crashes. And also, the second demo, it's just a very simple example what you can do with it. So on the right, left side for you, on the left, this is the attacker point of view. And on the right, this is the SAP process list. So you can see this is whole SAP process list. So the gateway, the dispatcher, etc. And what is possible to do is to send this packet. This is only one packet remotely without any authentication. You send one packet on each services and you can crash everything. And so just make a very simple Python script. You provide the target, you send it, and on the right you can see the process disappear because everything crashed. And trust me, it's not very easy to restart an SAP system after that. All right. So, as a conclusion, I put all the components involved in the vulnerability we find. As you can see, there are a lot of components. So if you run one of these components, please update it. And the interesting thing is, yeah, but basically, the impacted component is hold the kernel. Hold the kernel on every system, Unix, Windows, everything, 32 bytes, 64. Hold the kernel is impacted. Everything is patched since last year, I guess. So the SAP create bundle patch. So in one patch, you have several vulnerability collected, and they create one patch by services. This is just a timing, very timetable of the research. So we start in July. Again, we start from 0. I did not know nothing about fuzzing and fuzzy area, so it was the step was not easy at the beginning. And yeah, we find crash for 2 months. Then we decide to stop, and I work on it like quarter of time for a few months again to study all the crashes, to try to figure out if it's easy to exploitable or not, and also to provide a very detailed report to SAP. So I put the reference, so the Fuzzertron, very cool fuzzer. And also I put in our GitHub, if you are interested, by whole, we put the advisory of whole crashes we find. So if you are interested to have more data on each crash, you can go to our GitHub. Also the SAP URL and the SAP response team again. That's pretty much it. For my point of view, this is an example to fuzz black box or custom protocol. I use SAP as an example, but I hope some of you can get it and hey, maybe I can do something on different target, not SAP related, but I can do use this kind of idea to perform some other fuzz on other network. So that's it. And of course, I haven't explained all the little problem we get. I just keep what we think it was the most important. So thank you to Dori for Fuzzertron. Thank you to SAP and SAP security team. We have a good relationship. When you send 20 vulnerability in one time. This is not is not usual. And so thank you to invite me.
Thank you, Yvan. I looked a little bit online, saw no questions there. Are there any questions from the room? Anybody? So yeah, I of course do have some questions here. So you had so many bugs. Did you also try to see if you could get some remote code execution out of that? That's of course an interesting question.
Of course, we try to study each bug and to find out if it's possible to exploit them to have some remote code execution or something like that. But you can imagine you are remote and completely blind, and also the architecture and the version can change a lot. And we decide to not spend too much time on it. So we try it. We are not the best of the world to try to exploit this kind of vulnerability, maybe, but after a few tests, we decide to not take too much time on it.
And do you maybe have some more information on what type of bugs these were? Were that memory corruption bugs? Were those command line injections, or what type of bugs were causing these crashes?
There are a lot of different bugs. It's sometimes very complicated, not very complicated, but it's real. But many times it's a nil pointer dereference, or sometimes also they use hard-coded offset in the packet to calculate something. So if you change it, it calculates the wrong place and try to allow the wrong size of memory and stuff like that. But we put the detail in our GitHub. In whole crashes, we try to put the detail of what kind of function crash, why, etc.
Okay, thank you.